Welcome students. This week we are going to talk about wave equation. Wave equation. So this is the second important equation which we study in this course on advanced PD, and essentially this is also an evolution equation. So let me write down the equation. The equation looks like this: utt, so double derivative with respect to t, minus Laplacian of u is equals to 0. Clear? So that is the wave equation. Of course, this is the homogeneous wave equation. If you want to write it like a non-homogeneous, let's write it G. Yeah. So this is an example of a non-homogeneous wave equation. Of course, when G equals to 0, that's a homogeneous equation. So let me put it this way. Number one, if G equals to 0, then 1 is homogeneous. Okay, and if G is non-zero, then 1 is non-homogeneous. Okay, so that is quite a known idea. Right, now let us understand the equation properly and then we'll go from there. So what is u? U is the unknown here, right? So the unknown, so let me put it this way, the unknown. So when we write an equation like this, what I meant by this equation is defined in some domain. We'll define all that, okay? But essentially, see, it is saying that inside the domain, inside some space set, u satisfies this equation. So G will be given to you. G is the known quantity, yes, and you are told that G is equals to utt minus Laplacian of u. You need to find what u use. That's the question. Okay, so the unknown function u, clear, that is from omega bar. Yeah, and for now let's just assume only omega is open. So I am going to only assume that omega is open. Okay, and later we will put some more assumptions on omega. Omega is open in Rn, let's say. Yeah, Rn. Okay, so the unknown function u is from omega bar. Omega bar is the closure of omega. Omega union the boundary, right? So times close 0, infinity, open. Clear? To R. Okay, and it is given by, so essentially you write it as u of xt. Clear? X is the Rn, x is in Rn, and t is of course 0 infinity. T lies in 0 infinity. Okay, so u is a real valued function, and the values, it depends, the domain is omega bar cross 0 infinity. Time we are always taking is on the positive axis, so that is why t is between 0 and infinity, and x is in Rn. Clear? Now also note that here it is exactly like the Laplace, heat equation which we did. See, in heat equation this Laplace, so here, so what is the difference between heat equation? See, heat equation will look like this: ut minus Laplacian of u equals to some G. So here the difference is this. This is the same thing. Heat equation, this is only u with respect to t, just one derivative. Here u is with respect to double t, so utt, so double derivative of u. Okay, after that everything is same. Okay, so but what is, so essentially this thing Laplacian of u in heat equation, if you remember, Laplacian of u is with respect to the spatial variable. Okay, so here also the same thing, the Laplacian delta, okay, is with respect to the spatial variable, with respect to the spatial variable. What does it mean? It means that spatial variable. See, here u depends on what variable? X and t, right? So if you are writing Laplacian in just a calculus sense, not a PDE sense, yeah. So in sense of calculus, so if you are doing just calculus, and you are given u is a function of x and t, and if I am telling what is Laplacian of u, what does that mean? It means that u xx plus utt. Let's say x is in R for now. Yeah. So it will look like this: u xx plus utt. So for x in R, let's say, it will look like this. So n equals to 1. Just take. That's Laplace in calculus, but in PDE, okay, in this case, in wave equation, not everywhere in PD, just in wave equation or heat equation, what we do is when we say that UTT minus Laplacian of U, let's say that is equals to 0 we are writing. So for n equals to 1, how does it look like? It look like UTT minus spatial variable here is the x. So this is with respect to x, Uxx equals to 0. Clear? Okay. So not, see, Laplacian of U has to be Uxx plus UTT. I am not taking UTT part. It's only the Laplacian is with respect to the spatial variable, in which case this is x. So this is only UTT minus Uxx. Clear? Okay. Sometimes, so we also write this Laplacian. So in some books you may find it. Yeah, most of the times in mathematical physics books, the wave equation, the wave operator is given like this: UTT minus Laplacian of U. We just write it. This is a shorthand notation. Sometimes we may write it, sometimes we may skip it. Okay, so that's there. Now you can see the similarity between these two operators. See, these are very similar looking operators, right? So what is one is UTT and one is UT. That's the only difference. Yeah. So the thing is, if what do you? I mean, if I'm just asking you, what do you think are the difference between these two? So let's say I want to study this equation, any solution of this equation and any solution of this equation. Do you think there are differences between these two? Yeah. See, I mean, this is a very vague, thing which I am saying, vague. Yeah, vague. I mean, idea. Let's just say. Yeah. So, how vague idea? So, in terms of solution, okay, vague idea. So, this is not any mathematics I am doing. This is just an idea for you to understand. So, in terms of behavior of solution, okay, heat equation and Laplace equation are very similar, whereas wave equation has a very different in the sense that different from Laplace and heat, different I mean attitude. Okay, let's just put it this way. So this is nothing, no mathematics here. I will just explain what the idea is. So what I'm trying to say is, see, here I am to explain this idea. What I meant here, I will use something which I did not do in this course, but since this is a more advanced course, I gathered that you guys already know what a canonical form is. Yeah, so essentially, you see, if in a canonical form, what happens is this: you have a equation like a second order equation, LU equals to 0, right? And based on the discriminant, you can say that whether it's the hyperbolic, elliptic and a parabolic equation, right? Now you see what is happening is this: you guys know that if now see the behavior. So let me write it like this. So let's say that's the second order, general second order linear. So this is second order, okay, linear second order linear differential equation, right? Differential equation. I'm not writing all that. This is just for you to understand what's going on. See, you guys know that the behavior of one depends on the higher order term, right? What I meant by this, what do I mean by this? See, what I mean by this is, you remember what is the discriminant? B square minus 4ac, that has to be negative, positive, or 0 based, I mean, depending on whether it is a elliptic, hyperbolic or parabolic equation respectively, right? Okay, so what we are trying to do is this. See, this equation, so let's say L of u, it will look like this, right? AUXX plus BUXY plus CUYY plus DU x plus EUY plus F plus FU plus G is equals to 0. That's the second order equation, right? I mean, L of u may look like this. Now, the point is this. See, after a canonical transform, okay, you do a canonical transform. what happens? After a canonical transform, you can reduce it to either hyperbolic, elliptic or parabolic equation, right? Laplace equation is an example of a elliptic equation. Elliptic equation, right? Wave equation is an example of a hyperbolic equation. Okay, hyperbolic equation. And heat equation is an example of a parabolic equation. Parabolic equation. Okay, now if you have understood what's the idea of canonical transformation is, then I am quite sure you understood what is going on here. See, essentially canonical transform says that the behavior of the solution of one depends only on the higher order. The lower order terms determine something but not much. You understand the main, the main behavior. It is not very mathematical, but you understand what I'm trying to say here. Okay, see the behavior of the solution does not change. You understand? I mean, if you remember, while doing higher, this canonical transform, you have reduced it to some canonical forms, right? Okay, for elliptic equation, the form was like something like this, right? W xi plus W eta equals to some lower terms of W xi, W eta, W, and some this is for the elliptic equation, right? Something like this. I'm not writing all that, you guys already know. So for wave it is W xi eta, something like this, W xi eta plus some lower terms, something like this. This is hyperbolic. So, but the thing is, what I'm trying to suggest here is this. See, essentially, what is important is this second order term. There are lower order terms, but that does not, drastically influence the behavior of solutions. You understand what I'm trying to say? So, you see, what is the difference in Laplace equation? The thing is the utt plus uxx. So, uxx plus uyy equals to some function. Okay, so the higher order term is uxx plus uyy. Here also in heat, the higher order term is uxx plus uyy. Of course, there are lower order terms ut and all, but the thing is higher order terms is this. So heat and wave, a Laplace equation, they have the same sort of higher order terms. Okay, so the behavior is kind of same. You understand what I'm trying to say? But here the higher order term, you see their sign a change, different. Okay. So there's a positive, there's a negative sign. So that what happens then is the behavior of the solution changes. You understand? That is why the behavior of the solution changes. And how it changes, so let me put it this way. Okay, this also we will prove it later. Okay, for now it is just for your information, just for you to understand what is going on. Okay, because you see in heat equation this term is there, but that's basically a lower order term. So essentially this is a Laplace equation. If you think about it, this is just you understand, extension of this elliptic idea. Okay, heat equation. So basically heat and Laplace are closely knit together. Okay, so once you understand the good understanding of Laplace equation, heat actually can be many properties of heat equation can be derived. So that is what we did in heat and Laplace. Okay, but for wave equation everything falls apart. Okay, because the whole operator is different. Okay. So let me just write it down. What difference can you think of, and then we'll go from there. So for example, okay, let me put down the example first. Number one, you see, generally for wave equation, okay. So for heat and Laplace, I don't know, maybe I can do it in the next page. It will be better, I think. So let me put it like this. Sorry, heat by Laplace, okay, and wave. So let me put some differences here. So the first difference is the solutions which you are going to get. For let's just assume the homogeneous problem, okay, assuming homogeneous problem, okay, homogeneous problem. See, here I am assuming the most simple model, okay, because that will actually help you to distinguish. Even if in the most simple model these are different, then definitely they are different elsewhere, right? So let's just assume most simple problem. Don't worry about all the complicated examples, just the basic problems. For a heat equation or a Laplace equation, you know that the solution is C infinity, right? Okay, you know that the solution is C infinity. In wave equation, U is not in C infinity. Okay, of course in some cases they will be, okay, not in general. In general, they are not. Clear? Okay. Number two, let's say, for bounded domains, of course, bounded domains, okay, mean value theorem works. Okay. Here, mean value theorem does not work. Okay, does not matter bounded, unbounded, whatever it is, mean value theorem does not work. Here mean value theorem does work. Okay, right. Now for Laplace heat equation, we have seen something like a finite or infinite speed of propagation, right? What is infinite speed of propagation? So if you start with a positive initial data, that will get carried over for all times, right? Okay, so for heat equation, heat I don't know, admits, let's just put it this way. This is not very mathematical type of writing, but I mean, you understand. So it exhibits, let's say, yeah, not admit, exhibits infinite speed of propagation. Yeah, we talked about it. What is infinite speed of propagation? Now, here in wave equation, this exhibits finite speed of propagation. Okay, propagation. Now I will explain to you what finite speed of propagation is later when we do this. Yeah, don't worry about it all that, but the thing is, you understand that there are some basic differences. Yeah. Okay, so that's heat Laplace and versus wave. So wave is a totally, this is like the wild card of this family. So we are studying this family of equation, right? Heat, wave, and Laplace equation. These are second order linear equations, important second order linear. Okay, but heat and wave are like different beasts, and wave is a different animal. Okay, right. Now let's look at some physical interpretation, and then we'll go from there to understand what's how to solve this kind of problems. So physical interpretation. Okay. So see, generally wave equation, as the name suggests, you understand that this is a wave, right? I mean, this is something to do with wave. So basically, if you study a light, sound, okay, all of these are essentially wave, right? Okay, so this is a very fundamental equation to study. Okay, for n equals to 1, let's say n equals to 1, what I meant that, see, time is always in one variable. I mean, you can't change time, right? So here the only thing when we are writing n equals to 1 is essentially the spatial variable. So for n equals to 1, it actually models the vibrating string. Okay, vibrating string. Okay, and for n equals to 2, it actually models those tablas and those instruments, how do I put it, drums and all. Yeah, so those are some kind of membranes, right? So for n equals to 2, if you want to model the vibrations of the membranes, then this is vibrating membrane. They are modeled by this equation. Okay. Okay, let us do that, and let's see what this physically means. Yeah, let's do it physically more in a nice way. Okay, so first thing first, what is u? See, in these physical situations, what we do is we will write u of xt. What u of xt does is this represents, okay, this represents the displacement okay, in some direction. Of the point x, at the time t, greater than 0. Clear? So basically, you see, a point is moving, yeah, it's moving in some wave kind of, you can think of. Okay, so point is moving. Now I want to see, so what does you do? You represent what is the displacement, how much it moves, okay, in which in some direction it is moving, okay, at so let's say this is the point x, so I want to see how much x is moving in some direction, okay. So the displacement of u, okay, I want to see the displacement of u in some direction at a point x and a time t, okay. So that's u. Now let v represents, so basically this let's say this wave moves in some particular region, and let's say v represents any smooth subregion of omega. Clear? Okay, so omega is a region, or I mean, if you want, you can think of the whole space, yeah, and v represents a subregion of omega. Okay, so what is the acceleration within v? Acceleration of the wave. Now the acceleration of the wave, okay, the acceleration of wave within v is given by this, right? See, it is essentially u dx, the double derivative of this. Acceleration is double derivative d dt square, okay, of this. Clear? Okay, and that is given by integral over v u dt dx, because this integral is with respect to x, so I can take the time variable inside, okay. And the net force, okay, so net force which is acting, that is given by minus integral over the boundary, so on the boundary of the domain, the v, okay, this is f dot gamma ds. Yeah, so what is f? F is the force acting on v through del v. Clear? Okay, and gamma, there is also a mass density here, okay, that I am taking to be, so this is the net force, okay, the net force is this, right. And so essentially what is happening here is this. See, Newton's law, yeah, that says that mass times acceleration is net force. This is the net force, okay. So you see, at every given point the force is F, okay, outside. So you see that, let's say that's your V, and at any given point in V, okay, the force is is given by F, okay. So in the whole boundary, if you want, then the force is given by F dot gamma. Gamma is the unit outward normal, okay, given gamma unit outward normal. Okay, so the net force is given by the integral of f dot gamma. Clear? Now, and so essentially what is happening is this, from Newton's law. So therefore Newton says this force is equals to mass times acceleration, right? So this is equals to integral v, so mass is, let's say, 1, that we assume, that mass is, let's say, 1. So basically this is utt, okay, dx equals to minus del v f dot gamma ds. Clear? Okay, and this implies that one second, fine. So this is equals to minus integral over v. See, this is via Gauss divergence theorem, okay. So integral over v, divergence of f, okay, dx is given by integral over the boundary f dot gamma ds. That's Gauss divergence. Yeah, we did this earlier. So you have, for any smooth subregion v, integral over v utt equals to minus integral over v divergence of f dx. So what does that say? For for any smooth subdomain V inside omega, this is true. Okay, so it means that UTT has to be equals plus divergence of F has to be equals to 0. Clear? Okay, because since this holds for any sub-region V, smooth sub-region inside omega. Okay, now if that is true, then now generally what happens is for small, so how do I put it? Generally, for the vibrating string or membrane kind of cases, what happens is F is assumed to be in general, F is assumed to be proportional to the displacement gradient. Okay, be proportional to the displacement gradient. Okay, what I meant by this, so basically what I meant is f of gradient of u, that is essentially minus some constant times gradient of u, something like this. Okay, so therefore if you put it all together, therefore it means that it will give you UTT. If you put this f here, it is some constant times u, the divergence of gradient, that is Laplacian of u. Okay, so this is C Laplacian of u equals to 0. So that is your wave equation. Clear? Okay, so that is the physical interpretation of what wave equation is. Yeah. Now, as you know that this is our common, strategies to study any PD. What we do is we are going to study. So once we understand that how it is coming, okay, the common strategy. Now the common strategy to study wave is look for the well-posedness. Let's see if we can look for the well-posedness or not. So if the problem is well-posed or not, is well-posedness. Okay, so that's the common strategy. We want to see whether this is, we don't know. Okay, this is what we need to find, whether it is well-posed or not. We have seen that Laplace equation, let's say in a bounded domain, that's a well-posed problem, right? Okay, here also we are going to do something similar. We want to see whether they are well-posed or not. Okay, so for that we again start with the the basic one. So first of all, for well-posedness you have existence, uniqueness, and the continuous dependence of the data, right? Those things are there. But here again, in the same way which we did earlier, we are going to start with the energy methods to show the uniqueness first. Okay, so we are going to study some properties of the solution. Okay, so we are going to start with something called the energy method first. Energy method. Okay, now to do that, first of all we have to understand what the domain is. First thing first, so we assume, so let omega subset of Rn. Okay, so first of all what we are doing, we are talking about uniqueness. So first question is uniqueness. We are going to talk about uniqueness of solution. Okay, for the well-posedness part, we first start with the uniqueness. So let's start with omega, which is subset of Rn, be open. Of course that is open, we are assuming open, it's already assumed, bounded domain with a smooth boundary. Okay, of course they are always assumed with a smooth boundary. Clear? So that is always there. As usual, we will assume also omega t. Okay, omega t is omega cross open 0 t closed. Clear? open 0, t closed, and gamma t is omega t bar minus omega t. Okay, so what is omega t? Omega t, so let's say that's your omega, and this is your the cylinder kind of thing where all of this is happening. Okay, so exactly the same thing here. My drawing is very bad, so that is why it looks like this. This is t equals to 0. Okay, and this is t equals to capital T. Okay, so omega t is omega is whatever is inside, not the boundary. Okay, times 0 t. This 0 t equals to 0, so the base is not there. If you remove the base, everything else is there. Okay, with the top part also, the top hat is there. Of course, this line is not there. Okay, the top hat is also there. So that is omega t. Gamma t, you take everything. Omega t bar is the whole cylinder, inside, outside, whatever you can see. That is also there, inside is also there, everything is there, omega t bar, and you just take the omega t out. Okay, omega t out, so that's your omega t. So only this vertical sides are there and this base is there. Okay, that's his omega t. So this, of course, this t is capital T is greater than 0. We are all, that is general assumption. So that's this thing. Now we are going to write first thing first, the initial and boundary value problem, how all of this looks like in the context of wave equation. Let's write down. Okay, maybe I can do it in the next page, it will be better, I think. So the initial slash boundary. So see, these problems are not only initial value or boundary value problems, but both initial and boundary value problems. Okay, so in OD, you guys already, when we do, we just write it as initial value problem, boundary value problem. Here they are both. Okay, and they look like this. See, utt minus Laplacian of u, this is equals to f in omega t. Okay, so of course that is always there. That is the wave equation. What does u do on the boundary? That is equals to g on gamma t. Clear? And so see, on the boundary, this is not the parabolic boundary, please remember, this is the wave for boundary of for the wave equation. Gamma t, in gamma t, what does u do? U is g. Here this is difference between wave and heat equation. In wave equation, this is enough, this is the initial boundary value problem, but here you need the information on ut also. Ut, that has to be equals to h. Okay, on omega base, t equals to 0. Okay, I need to know what ut does on the base, because I have to deal with utt also. In the other case, it is just ut. Here I have to deal with utt also. That is why I need this information on ut on the base layer. Okay, while t equals to 0, and that is ut is equals to h. Okay, now with this, what we are going to do is we are going to prove a theorem which is like the uniqueness. Okay, so this is the uniqueness for wave equation. So what does it say? It says that, let's say that's your problem, let's say that's your 1. Okay, so there exists, see, since I did not prove that there are solutions for this problem, I will assume that if there are solution, this uniqueness says that that is the only one. So it says that there exists at most one function u in C2 omega t bar, okay, which solves 1. Okay, one small detail which I missed is this. Whenever we say solution of 1, what do I mean by solution of 1? Let me, so excuse me for this one, because I somehow missed it. What I am going to do is, before I, so this is a theorem, yeah, this is a very important theorem, uniqueness. Before I go on with the proof of this uniqueness, let me tell you what is the solution of this, yeah, because in heat equation we saw the solution is C21 omega t, yeah. Here what is the solution? So before I move on, Please excuse me for this one. So I want to write it, so maybe I can put it in a box. Put it in a box. Okay, so a function u, okay, which is C2, clear, of omega t bar. Okay, so this function is said to be a solution, of one if it satisfies every condition, these three conditions. So if it satisfies one for all xt in omega t bar. Clear? So first of all, you have to have a solution, you have to have a u which satisfies all these three. So u satisfies one essentially. And where does u lie? U has to be C2 in omega t. C2 in omega t, it means it has to be twice differentiable with respect to t and twice differentiable with respect to the spatial variable x. Okay, see, in heat equation, okay, heat, you have u is C21. C21 is 1 with respect to time, 2 with respect to spatial variable, right? Because ut is already involved. But here in wave, what happens is you have utt minus Laplacian u. So both utt has to exist and Laplacian of u has to exist. So u has to be C2. Okay, C2 in both variables. Okay, so that is why it is C2. Okay, that's your function though. Now let's talk about uniqueness. Okay, uniqueness. Right. Proof. Now, proof. What I am going to do here for the proof of uniqueness, I am going to use something called the energy estimate, which we already did in other cases also. Okay, in the case of Laplace, in the case of heat, here also we are going to do something similar. So let us assume, let u tilde be any other solution, okay, any other solution of 1. Okay, now you set w equals to, see, I am doing usual stuff, so you assume two solutions and you show that it cannot happen. Okay, so let's say, one sec, sorry about it, so let w equals to u minus u tilde. This solves. So if you set this, then if you set w equals to u minus u tilde, then w solves what? Then w solves, okay, this equation, wtt minus Laplacian of w equals to 0. Why this is happening? Because you see, this is a linear equation and f minus f will become 0. This is a linear equation. So u, if you change it to u minus u tilde, nothing changes. It becomes wtt minus Laplacian of w, because Laplacian is also a linear equation, and f becomes f minus f, which is 0. And the similar thing with the boundary conditions also. So this is true in omega t, okay, and w equals to 0 on gamma t, and wt is equals to 0 on omega cross base. So please remember the boundary condition, the initial condition, yeah, this is the base condition on omega. That is wt, the information on wt is given only on the base, not in the vertical sides and all. Okay, so wt, right. So w satisfies this thing. That is very easy to see. I mean, I am going to skip this part. This is very trivial. Now what we are going to do is we are going to define the energy of the system. Okay, so this is very physical. So define the energy of the system. Okay, energy Et. You remember we did something similar in wave equation also. Et, that we are going to define here as half integral omega wt wtt, okay, plus gradient w dot gradient wt, okay, and dx. Clear? Of course, here see this where does all of this comes from? If you are interested in understanding where this energy functionals and all this, this is called the energy integral or energy functional. I mean, in many different places different names are there, but how all of this is coming and how we work with all of this, this can be found in any book with containing calculus of variation. Okay. Any book on calculus of variation will actually be able to tell you how all of this works. Okay, so I'm for now, let me you can use Evans. There's a PD book of Evans, right? In that book, calculus of variation, the chapter 8, I think 8 or 9 something is there. 9, chapter 8 probably, chapter 8 or 10, whatever, or 10, I am not quite sure. Okay, so you can look at there, but there is another book called the Cornea, that also you can look at. So essentially, energy of the functional is given by this, energy of the system, is given by this. Okay, sorry, what am I writing? Sorry, this is all wrong. I skipped one line. So the energy of the system is given by Wt square xt, okay, plus gradient W of xt square dx. Okay, this is for 0 less than t less than capital T. Okay, so the energy of the system is given by this Wt square plus gradient of W square dx. See, energy, we are always assuming, we define it like this, that by definition at the base point this is going to be positive. Okay, so we define it like this. So if we do something like this, now see W, see U and U tilde, they are C2 of omega t, clear? So therefore W is in C2 of omega t. I guess this is fine. Now if W is C2, Wt is C1, you are taking an integral of a C1 function, that is C2 again, fundamental theorem of calculus, and again gradient of W is C1, square is also a C1 function, taking an integral, that is going to be C2, so the whole thing is C2. Et is definitely then differentiable, you can just prove. Okay, if you are not convinced, you can show that clearly E is differentiable. E is differentiable, clear? And what is the derivative? And E prime of t, that is given by, I can take the derivative inside here, okay, that is given by W 2 Wt of xt and Wt with respect to t, so that is W tt of xt, okay, dx, let me write it, plus, see, there is a 2 and a half, that's why this half is there, so it's cancelled out. So basically maybe I can cancel it out, it will be better. Integral Wt, okay, so this half, 2 and a half is getting cancelled, and again this is on omega, this is on omega. Again, if I do this thing, it is gradient of W dot gradient of W t dx. Okay, see, first thing is you just derive this thing, and the next time is you derive this with respect to t. So because of the continuity, I can take this inside, to it becomes gradient of Wt. Yeah, please, again, these I am calculating, I am just writing it directly. If you are not convinced, do it yourself. I will actually urge you to do it yourself, just check it. It's not very difficult to see, yeah, but that will make it all the more precise, so you will understand what is going on inside. So integral over omega, if you write it, this thing, you see, if you make a change of variable, this derivative I can push it here, so it becomes Wt. Okay, sorry, this it becomes Laplacian of W, okay, so let me write it, this is Wt minus Wt Laplacian of W, okay, dx. it becomes this. Yeah, why? Because I can just integration by parts. There's a negative sign will come, this negative sign, and one derivative goes here, so it becomes Laplacian of w, it becomes wt. What about the boundary? Boundary w is 0, so basically there is no boundary. Okay, so in the boundary w is 0, and hence the boundary term is not there. Okay, if you do integration by part, the boundary term is not there. Sorry, wt is 0, right? Wt is 0, so you can just put wt is 0 there, and you are you do not have that boundary term. Okay, w and wt is both 0, you see, on the boundary, so you do not have worry about that. Okay, so this is via integration by parts. Integration by parts. Again, if you are not convinced, do the integration by parts. It will one derivative will go there, and then you have a boundary term. The boundary term is becoming 0, so you are only left out with the term which is in the domain omega, right? So it becomes like this. And this, if you want, you can write it as integral over omega wt and wtt minus Laplacian of w dx. Wtt minus Laplacian of w is 0 in omega t. So in omega it becomes 0. So this is 0. Clear? Now, okay. Now there are no. See, what is happening is this. Since w is 0 on gamma t. Okay, gamma t, and therefore we have, if you take the derivative of w with respect to t, wt, that is going to be 0 on the boundary del omega cross 0 t. Yeah, I hope that is fine. This is fine. Since w is 0 on the gamma t, w with respect to t, that is also 0. Yeah, okay. Thus, for all 0 less than t less than capital T, okay, Et is equals to E0, which is equals to 0, right? Because you see, E prime of t is 0, okay, that will give you Et is constant. Yeah, what is E at the point 0? E at the point 0, if you see, this is Wt. See, what is E at the point 0? Let's check here. E at the point 0, okay, this is Wt at the point x0. Wt at the point x0 is 0, okay. So this is half integral 0 square plus gradient of w square dx. Okay, so gradient of w at the point x0. W is 0. Okay, w is 0 on, this gamma t also contains omega cross t equals to 0. So basically, omega w is 0 on omega also, omega cross t equals to 0. So what is the gradient? Gradient at the point x0, t equals to 0, x0, that is also 0. So basically, this is also 0 square. So essentially, E of 0 is 0. Okay. So E of t equals to E of 0, because E is constant, E prime of t is constant, right? So E is constant, so E of t is equals to E of 0, which is equals to 0. E of 0 is 0, this is what we just calculated, okay. Therefore, and hence Wt and gradient of w has to be equivalent to 0 within omega t, okay. Why? Let's see. See, if E of t is actually equivalent to 0, this is the integral of square. So these are the square of two functions, the integral of which is 0. So basically, those functions individually has to be 0 for this thing to make sense, right? Okay. So what does that mean? So since you see w is 0 on omega cross t equals to 0, that is true, right? W is 0. What can you conclude? See, Wt is 0 in omega t. Yeah. So what does that mean? It means w is constant with respect to the time variable. And again, gradient of w is 0 within omega t. It means omega is constant with respect to the x variable, right? Since omega, sorry, not omega, w. Wt is 0 means w is constant with respect to the t variable, and here gradient of w is 0 means w is constant with respect to the spatial variable x. Since w is 0 on the base omega cross t equals to 0 and w is also a continuous function, that will actually imply that w has to be 0 in omega t. Okay, so w is 0 in omega t, and that implies that w is u minus u delta in omega t. I hope this is fine. Yeah, this should not be a problem here. Is this clear? So inside omega t, see omega t is a connected thing, right? So omega t, w is constant essentially everywhere, and on the base w is going to be 0. Yeah, so w has to be 0 everywhere, right? For the continuity thing to hold, right? So that is why w, which is u minus u delta, is omega t, and that is equals to 0. So essentially u equals to u delta in omega t. Clear? And hence you have this what do you call uniqueness. Okay, so with this we are going to end this lecture.